Have you ever heard your speakers making that weird buzzing sound right before your phone rings? Well, that's electromagnetic interference, and it happens when one device signal accidentally leaks into another when it's not supposed to. And understanding how to prevent it is exactly what my research is about. Hi everyone, I'm Paola, a Marie Curie PhD researcher in the NEPIC project, and today I'm going to show you how we are rethinking the way devices are being tested. Every second, millions of electromagnetic signals are exchanged around us, from phones, cars, routers, satellites, and dozens of devices we don't even think about. So when we create a new electronic device, we have to be sure it can still work even in noisy environments. In order to test the device, we have to conduct some EMC testing, and we usually expose the device to only one clear signal at a time, something that almost never is experienced outside of the lab. Think of it like pointing a perfect straight flashlight beam at a device. It gives us precise measurement, but only for the specific situation. Inside cars, airplanes, buildings, or equipment housing, electromagnetic waves bounce around, interact with materials, and arrive from all directions. Cables are never routed in straight lines. Objects move, materials absorb energy. In order to capture all this behavior, we need test environments that recreate these complex and chaotic conditions. And that's exactly what a reverberation chamber is designed to do. Instead of producing one clean wave, it creates a rich, multidirectional field, very similar to what devices experience in real life. By moving the stirrer, changing its shape, or adjusting the chamber setup, we can generate thousands of different fields, conditions in a very short time. This flexibility lets us test the device in many different situations. But here is the interesting part. Inside the reverberation chamber, there isn't just one way to run a test over a device. There are many. So which method works best? Which one actually tells us the most about how a device behaves? And as electronics become more and more complex, it makes us wonder, are our testing methods still enough? To explore these questions, we test devices under many different conditions. For example, we study what happens when the device is placed inside a metallic enclosure, when there is an aperture that leaks fields inside, or when absorbing materials change how the energy behaves inside, or when nothing is as perfect as it is sometimes considered in theory. That's why our goal is to look at different approaches and ask, which one really captures real-world behavior? Or how can we make this test even more better for modern systems? What we do is we usually measure things like how the signal spreads out over time, how long it takes to fade, and how much energy gets inside the structure or is lost along the way. There's where the real excitement begins. We test in the labs, we run simulations, and then we try to validate new models by comparing both. By comparing all the new methods, considering realistic scenarios, and helping develop improved approaches, our work supports bringing EMC testing closer to real life and helping the community in creating testing procedures that are more realistic, more reliable, and more industry-ready. So that's a part of my work within the NEPIC project, helping us understand and improve how we test electronic systems in the real world. Thank you for watching and keep following us for more insight into the future of EMC testing and reverberation chambers.